Bismillah ar-Rahman ar-Rahim. So let's start our today lecture. So in the previous lecture, you have learned about the three quantum numbers, and first was the principal quantum number, second was the angular momentum quantum number, and third was the magnetic quantum number, and this is the last and the fourth quantum number, and it is called the spin quantum number. So after finishing this quantum number, actually we will move to the electronic configuration, because the knowledge you are getting from all these four quantum numbers we will be using to place the electrons in the relevant orbital. So that's why this information or the knowledge is must when you are going to proceed towards the electronic configuration. So main objective of today is the electronic configuration, the placement of the electrons in the shells, subshells, and the orbitals. And this is the fourth quantum number, and it is called the spin quantum number. It is shown by the small m, small s, and actually this is the another principle which is defining that no two electrons in an atom can have the same four quantum numbers. The quantum number, the principal quantum number, or the angular quantum number, or the magnetic quantum number may be the same for the two electrons present in a orbit, but there must be the difference in the fourth quantum number, and that is the spin quantum number. So the spin of the electron may be different, and that is the difference in the spin quantum number. So I'm going to explain first, to explain what is the spin quantum number. Actually, this is the electron, and electron may move in a clockwise rotation in an axis, and it may rotate in anti-clockwise around an axis. So when it is rotating like in this direction, it is going to generate some sort of the magnetic field, and this arrow is giving you the direction of the magnetic field. So when there is the movement of the electron, there must be the generation of the magnetic field, and this quantum number is actually is giving us the what is the direction of the magnetic field. And when the electron is moving clockwise rotation, then this would be the direction of the magnetic field, which is shown in the with the green color. And if it is rotating in anti-clockwise rotation around an axis, then the direction would be towards this, and as shown with again with the green arrow. So when it is going to be clockwise, we are going to show with this is having the minus half sign, and when it is the anti-clockwise, it is shown by the plus half sign. So here, these are just beyond your the course content. Here you just remember, if there are two electrons are present in an orbital, then the direction of the one electron like this, and this is the clockwise direction, and here the other electron having the direction like this, and this is called the anti-clockwise direction. So that is the difference in the fourth quantum number, that is called the spin quantum number. So the first three quantum number may be the same for an electron. Let's suppose if there are two electrons, so principal quantum number may be the same, and the angular quantum number may be the same, and the magnetic quantum number may be the same for the both electron. But this fourth quantum number should be the difference, and because one is having direction upward and one is having the magnetic field direction downward. So this is actually called the spin of the electron is different for the both of the electrons. One is having the clockwise rotation and one is having the anti-clockwise rotation. So this is all about our fourth quantum number. So let's I know I am going to conclude what we have learned in all four different quantum numbers. So this is just to refresh your knowledge, and you may consider this is all about the conclusion of what we have learned in four different quantum numbers. So I'm starting. We started with the shells, and here this is actually the principal quantum number that is shown by the small n, and these are the subshells, and as we have shown with the small l, and actually this is the angular momentum quantum number, and these are the orbitals, and here it is shown by the small m, and this is the actually the magnetic quantum number. So one is left, that is the our spin quantum number, and spin quantum number is just actually giving you the different spins of the electron. One it is having clockwise and other is one having the anti-clockwise. So which is not indicated over here, but the number of electrons are written over here because these electrons we are going to place in different orbitals. So I am just repeating what we have learned in four different quantum numbers. So starting with the one, when the principal quantum number is one, then the angular quantum number, it is shown by this very simple formula n minus 1. So 1 minus 1 will be 0, and number of orbitals will be 2 multiplied by 0 plus 1, it is again 1. So we are starting here for the magnetic quantum number starting with the 0. That means only one orientation is possible, and when it is 0, it seems there is the spherical shape of the orbital and there is no specific orientation. That means it is having the spherical shape of the orbital. And this we have done in the previous lecture. And what is the orbital notation? This is called the 1s. 1 is coming from the principal quantum number, and when L value is 0, that is called the s, and with this notation, this is called the 1s orbital. So number of orbitals in subshell are only one for this case because only s orbital is present. That's why the number of orbitals in the subshell is one, and the number of orbitals in the shell, this will also be one. So this is the first case because it is only the s is present in the k shell. So, and you can also calculate the number of orbital by using this formula. This is the n square, and here n is 1. So 1 multiplied by 1, it will remain 1. So maximum number of electron present are 2 over here. And there are two ways to calculate the number of electron. One is you can also use this very simple formula. So one, it is we are talking with n1 when n is 1, and 1 multiplied by 1 is 1, and when 1 multiplied by 2, it will be 2. So there are maximum possibility of the electrons in the s shell is the 2. Or you must remember there is always only the possibility to occupy only 2 electrons in each orbital. There is no possibility to occupy more than 2 electrons in each orbitals. So you must remember this formula also. So let's moving to the second, so it will be more clarified to you. So when we will move to the another quantum number, that is the L shell, and here the value of n is 2. And in this case, when you have calculated, so I'm not going to repeat again all these steps because we have in detail we have discussed in the previous lecture. So here the angular quantum number would be the value of 1, and you have to proceed to the 0. And here again, when it is 0, this will remain 0, and the the orbital notation for this one is 2s, because 2 is here, n is the principal quantum number, and when s is l value is 0, then it is called the s. Again, there is one orbital, and total number of electron present in this orbital will be 2. So I will be moving to the rest, the four, how it is coming out. So second one is the when the value of L is 1, so M value will be 0, 1, plus 1 and minus 1. And this is indicating that this is the 2p, 2 is coming from N and P is coming from the value of L. When value of L is 1, that is called the p orbital. And again, the number of orbitals in the p shell, there are three, and actually this is the magnetic quantum number which are giving you the information. There are three orbitals in this subshells, and one, two, three, that's why it is written over here, three. So total number of orbital in the shell, actually shell is the two we are talking about. So 3 plus 1 is the total number of orbitals present in the second shell, and that's why total number is 4. And you can also calculate by using this formula, 2 multiplied by 2, that will be equal to 4. And when you multiply by again 2, the number of electron would be 8. So actually number of electron would be the double of the orbitals present in the shells. So there are 4 shells, so the number of electrons would be 8. That means double to this one, or you may also use this formula to calculate the number of the electrons. So moving to the third one, so I will just explaining one again. So if any one of you have did not attend the previous class, so it's better to understand over here. So when your shell is 3, then L will be 2, so you have to move to the 1 and then to 0. When value is 2, then by using this formula, there are 5 orientation: 0, minus, plus 1, minus 1, plus 2, minus 2. And this orbital is called the 3d. 3 is coming from the shell and d is coming from the 2. When L value is 2, that is called the d. And how many orientation are there? There are the 5 orientation, or you can say these are the 5 orbitals of present in the d subshells. So because 1, 2, 3, 4, 5. So actually this information, the magnetic quantum number is giving you how many is the possibility of the orbitals present in the subshells. So when it is 1, again similar to this condition, this will be the p. And but here we are talking about the n principal quantum number 3, that's why it is the 3p. And there are 3 orientation, because 1, 2, 3, there are the 3 orientation, or the 3 orbitals of the p subshells are present. So total number of the orbitals in the shell, that means in the third shell, total number of orbitals are 5 and 3, 8 and 1, 9. So there are the 9 orbitals. And how many electrons are there? Double of the 9 is the 18, or may you also use this formula to calculate the number of the electrons. So we are talking about the third shells. 3 multiplied by 3 is the 16, and so 3 multiplied by 3 is the 9, and then 9 multiplied by 2 will be the 18. So by using this formula, or you can also double uh, the number of the orbitals present in the shell. So because maximum occupancy of each orbital to contain the electron is 2, that's why the number of electrons would be double to the number of orbitals present in the shell. So actually this is all about the conclusion what we have discussed in the previous lecture. And right now, before this slide, now I am moving to the to apply this knowledge. So this would be very interesting. Now you are going to place the electrons in the different orbitals. So starting, so which orbital would be occupied first? And these are the, as we you have learned in the some of the previous lecture. So there are the four blocks. This is the S block, this is the P, and this is the D block, and this is the F block. So if one electron is there, so how can you occupy, which orbital is going to first fill to be filled with the electrons? And this common understanding is which is having the lowest energy. The first one electron is coming with the orbital which is having the low energy. So low energy, as indicated over here, the first energy, the n is any of the principal quantum number. Let's go 1, 2, 3, S. So S is having the least energy, then it is P, then it is D, and then it is F. So this is the increase in energy level. So first electrons come to the S orbital, then it will go to the P, and then go to the D and the 4. But this is the detailed description about the placement of the electrons in the orbitals. So you have to start from here, and here this is the hydrogen, this is the helium, these are belongs to the first S. Then it will go to the there 2S, 2P, then 3S, 3P, then 4S, 3D, 4P, 5S, 4D, 5P, and so on. And here it is written with the arrow. I started with the 1S, so it will going to start with the 1S, then these are the 1S, then it will go to the 2S, then 2P, it is written over here 2P, then 3S, it is 3S, then 3P, it is written over 3P, then 4S, it is 4S, then 3D, 3D, and 4P, it is 4P. So, so on. So you may remember by using the periodic table, or you may remember the filling of the electrons in the orbital by using this general representation, or it is more easier to remember by using this picture, and this is called the diagonal rule. So you just first place 1s, then increase one orbital in each line. So 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and increasing 4f, and 5s, 5p, 5d, 5f, and you may put over 5g, but it is not going to fill that because not having placement in the periodic table. And then how can you remember which is going to be first filled? Just putting the arrow. So first electrons are coming to the first 1s, then put again arrow. This is going to the 2s, then again putting the arrow. So it is going to first 2p and 3s, and then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. And this is same what is written over here or in the periodic table. So if you forget during the examination, so just put this the diagonal rule. So you can increase actually one orbital with the when you are moving to the rows. First as 2s, 2p, and then with the 3 you are adding 3d, with the 4 you are adding 4f, and just by putting the arrows you can decide which is going to be first filled up and then later on. So this is very simple. I think you would be easily remember by using this formula to understand the electronic configuration. So let's move to the now filling of the electron, starting with the first one, which is the hydrogen. So this is the nucleus. Hydrogen is having atomic number 1, and you know atomic number 1 mean it is having only one proton. But here we are not discussing the protons, but we are getting the number of electrons with the consideration of the protons, because one proton, so there should be a possibility of the one electron. So our concern over here is the one electron. So this electron is present in the first shell, that is called the K shell, and you may say this is the principal quantum number 1. So value of n is 1. So this is the electronic configuration. First you have to put what is the this shell, this is the first shell, And in the first shell, as we have indicated over here, first is going to fill up this. So actually first electron will be coming to the first 1s. One electron is represented over here, or you may also put with this clockwise rotation of the electron, which is spinning around the axis, by representing with the arrow line. So what is written over here? So S is indicating you the orbital or the subshell, and one is the energy level, or you may say this is the principal quantum number, and this is the number of the electrons in this orbital, and this is all about the electronic configuration for the hydrogen. So let's move to the second, which is the helium. And helium atomic number is 2. That means proton are 2 and the number of electrons are the 2. So first, this is going to be filled up with the 1s. And I have said earlier that the maximum possibility of retaining the electron in each orbital is 2. So unless it is filled, the electron will not move to the second orbital. So because it is the maximum capacity of the s orbital or any orbital is 2, so first electron will come with the this direction clockwise, and then it would be the anti-clockwise. So you may also represent by using this simple notation or by using this. Actually, this is the all these three quantum number will be the same. So as we have learned today, the fourth quantum number will be the different, and two electron, one it is having the clockwise orientation and other one is having the anti-clockwise orientation, or you may say spin, positive spin or the negative spin. And here this is again represented as I have explained. This is give you the information level, this is the orbital, and these are the number of the electrons. So let's move to the third element and the fourth one. So this is the lithium, and here lithium and the beryllium. And the lithium atomic number is 3, number of protons 3, and the number of electron will also be 3. So in the first, how can you fill up the electrons? So it is the 1s, and then it will be 2s, and the two electrons are filling up with the 1s, and one electron is left that will move to the 2s orbit. So how have you written over this? This is again I am explaining again. You can get the idea. So first is 1s, then 2s, 2p, 3s, 3p, and so on. So you can easily calculate by using this diagonal rule if you forget whatever is the energy of the first or the second orbital. So again with the beryllium, beryllium atomic number is 4. So number of proton 4, number of electrons are 4. So first 1s is filled with the 2 electrons, and then with the uh, 2 electron will go to the second orbital, that is the 2s. So this is the electronic configuration of the beryllium. So moving to the the rest, from boron to the neon, from atomic number 6 to atomic number 10. So here actually you are going to start with the p orbital, because the first is 1s, then 2s, and then there is the possibility of the 2p orbitals. So how you are going to put, we have the three orientation of the p orbital, that means 2px, 2py, and 2pz. So you just remember, if you forget px, py, pz, so there are three orientation according to the magnetic quantum number. So because there are 0, plus 1, minus 1. So there are three orientation or three magnetic quantum number of the p orbitals, and these are the 2p, 2p, and 2p. And we actually differentiate between each p by representing the x, y, and the z. So let's start with the boron. So here I am first I am going to solve the first one, then I will actually do the exercise with you. So first one is the boron, and boron is having atomic number 5. So that means 5 protons and 5 electrons are present, And this is the electronic configuration for the boron. First electrons are going to the 1s, 2 electrons, and then these will go to the 2s, occupying with the maximum capacity 2p. And because the 5 electrons are there, so 1 electron is left, so 1 electron will go to the 2p. So this is the fifth 1 electron is going to the 2p, and there are the three orientation of the p orbitals, and that's why it is written over here. These are the three. So first one, second one, and the third one. So the next one is the carbon. I'm just filling one more. So carbon atomic number 6, number of protons 6. So the number of electrons are also 6. So what is the rule written over here? The 2 electron will go to the 1s, 2 electron with the 2s, and then because these three orbital have the same energy, so the first filling of the electron is with the clockwise rotation. First electron will go to here, then it will go to here, and then it will be going to here further on with the other one. So you may also represent with the 1s2, 2s2, or you may put over here 2p2. That is also correct. And you can individually label what is uh, the placement of the electron in each orbital. So with this one, I request some of you to fill the electrons for the nitrogen. So this is all about the electronic configuration. Actually, the meeting is going to be ended within 1 or 2 minutes. We have time, 6 minutes. So let's finish this one. So let's do the exercise over here. So any one of you can give me the electronic configuration for the nitrogen. So please do yourself as written over here, and then we will discuss later.